So once we have the mean value theorem, there's another theorem that follows along closely, correlates with it. So we call it Corollary 1 in our book. So basically, Corollary 1 says if you have a function whose derivative is always 0, then you know that function has to be constant. Okay. We know the opposite, right? If a function is constant, its derivative 0. Corollary 1 says it also goes the other way. If the derivative is 0 on some open interval, then the function will be constant on that interval. See, the proof of this follows from the mean value theorem. Here's what you want to do. Let's pick any 2 points, C and D, in that interval from A to B. This is a symbol. It means is an element of or is in. So we're just saying let C and D be in this interval, 2 points in this interval. And let's assume that we could name that the smaller one C. So let's assume that C is less than D. We pick 2 points. Whichever one's smaller, we name that C. The other one we name D. So let's assume that C is less than D. Won't affect that. Okay. Now, we have this function, and its derivative is 0 at every point in A, B. So its derivative also is also 0 everywhere at C and at D and at every point on D. So if it has a derivative, it's got to be continuous. So f is continuous and differentiable on the interval CD. Okay, so we have a function that's continuous and differentiable on the interval CD. Then by the mean value theorem, there exists a point between C and D. Since I've already used C for that end point, there exists a K between C and D, so it's strictly in the interval CD, such that f prime at K equals 0. Oh, sorry, f prime at K equals f of D minus f of C all over D minus C. Okay. So that's the mean value theorem. But we also were told that f prime at K was equal to 0. So this fraction has to be equal to 0. The only way a fraction can be 0 is if its numerator is 0. So f of D minus f of C must equal 0. So f at D has to equal f of C. So what we've shown is that if you pick any point, any 2 points between A and B, then the value of the function at those 2 points is the same. That means that the function can never change values, and therefore f is constant. So Corollary 1 says that if our function's derivative is 0 on some interval, then that function has to be constant. Once we have Corollary 1, we can get Corollary 2. Corollary 2 says that if 2 functions have the same derivative, then they vary by only a constant. So if you have 2 functions that have the same derivative, then the 2 functions can only differ by a constant. Now, the way to prove this one is to make this new function. We'll call it h of x. H of x is going to be f of x minus g of x. Okay, and since f and g are both differentiable, then so is h, because the derivative of the difference is the difference of the derivatives. But f prime and g prime are the same thing, right? So we're assuming that those two have the same derivative everywhere, and so that difference is 0. So h prime is a function whose derivative is 0 on this open interval AB, and so by Corollary 1, then h of x is equal to a constant. Is equal to a constant. So that means that since h of x is f of x minus g of x, f of x minus g of x is constant on AB, and therefore f of x is just g of x plus some constant. And that's what the theorem says, right? So we just assumed that this was true. The two functions had the same derivative on that interval, and we figured out that the hypothesis was true, that the two functions just differ by a constant. Now this is important because if we find the antiderivative of some function, we can be guaranteed by corollary 2 that if we find one antiderivative, all the rest are the same. There's not some other function that we haven't met yet whose derivative is also that value. All the other functions are just that function plus some constant. So we're guaranteed that there is really an answer to finding the antiderivative. Let's look at an example of using corollary 2. So we know that we have this function and it goes through the point 0, 5, because when you plug in 0, 5 comes out and its derivative is 2. So we know this, f prime of x equals 2. So one possibility that would be that f of x is equal to 2x. Of course, we could add any constant in and the derivative would still be 2. Our question is, are there any other functions that have that derivative? And because of corollary 2, the answer is no. They all, since 2x has a derivative that's 2, any other function that has a derivative that's 2 is just 2x plus a constant. So we know that there's just this possibility, there's just this family of functions to solve the problem. Now, in order to choose the constant, we could use this information that when you plug in 0, 5 comes out, because from what we found, we know that if you plug in 0, you get 2 times 0 plus c, which would just be 0 plus c, which would just be c. On the other hand, we're told that if you plug in 0, 5 should come out. So now we know that c must be 5 by comparing those two. So we can finish off the function. We know it should be 2x plus 5. We could always check, is the derivative of this function 2? Yes. When you plug in 0, does 5 come out? Yes. So we know that this is the answer to this problem. Okay, here's some more. Let's find all possible functions y with the given derivative. So if the derivative of y is 2x, well, can you think of any function whose derivative is 2x? Yeah, x squared. Could there be any more? Corollary 2 says if there are, they only differ by x squared from a constant. So there's all possibilities. What about this, 2x minus 1? Well, I know that the derivative of x squared is 2x, and the derivative of minus x is minus 1. Does this work? Yeah, if you take the derivative, you get 2x minus 1. So this is one possible answer. Are there any more? Well, corollary 2 says the only other possibilities would be to take that plus c. So there's the whole family of functions that solves this problem. Oops, I don't know why I wrote y prime there, right? Y should be x squared minus x plus c. Okay, now let's see. What about this one? Well, what would have a derivative that's 3x squared? X cubed has a derivative that's 3x squared. And we've seen above here, that 2x minus 1, you could get that from x squared minus x. Does that work? Well, take the derivative. The derivative of the sum is the sum of the derivatives, so we get 3x squared and a 2x, and the derivative of negative x is negative 1. Are there any others? Well, corollary 2 says if there are, they only differ from this function by a constant. So that finds all possible functions with that derivative. Let's do another one. Y prime is 1 over 2 times the square root of x. Let's see. So in other words, since I'm good at powers, maybe I'll write it in terms of powers. So in other words, it's 1/2 x to the negative 1/2. Do we know any functions whose derivative would be x to the negative 1/2? Since negative 1/2 is 1 less than 1/2, I'm going to guess that the answer is probably something like x to the 1/2. And I can check and see if it works. So I'm going to check right here. And y prime would be 1/2 x to the negative 1/2. Ah, that works. So the derivative of this is 1 over 2 root x, or this is the square root of x. Are there any others? Well, corollary 2 says if there are, they only differ by this from a constant. So I could just add a constant there, and I have my answer. All of the functions whose derivative is 1 over 2 root x have the form root x plus some constant. So there's my solution there. And this is pretty close. I could guess that y is root x again. But when I take the derivative, there's going to be an extra 1/2. So I don't want that 1/2 to be here, so I'm going to put a 2 in front. That's okay. I'm only off by a constant, and constants come through derivatives, so I should be okay, but let's just check. let's see, y prime would be, well, since this is 2 times x to the 1/2, y prime would be 2 times the 1/2 comes down, you get x to 1/2 power less, which the 2 times the 1/2 makes 1, so we just have x to negative 1/2, which is 1 over root 2. Yeah, that works. Okay, so y would be 2 root x. Are there any other possibilities? So the derivative of this is 1 over root x. If there was another function that had the same derivative, it would only differ by a constant. So by corollary 2, we know these are all possibilities for that function. Okay, we've got 2 that we can put together. We can see from what we did before that if we used a negative 2 root x, then the derivative of that, the derivative of 2 root x is 1 over root x, so the derivative of negative 2 root x would be negative 1 over root x. What has a derivative that's 4x? See, if I just used x squared, when I took the derivative, the 2 would come down and I'd have 2x, so let me put an extra 2 in there. What I'm doing basically is guessing at what the derivative should probably be. I know when you, if you have a power, every time you undo a derivative, every time you take a derivative, the power goes down by 1, so if you undo a derivative, the power ought to increase, and that's how I'm getting my guess. And then I just check to make sure it works. If I'm off by a constant, I can always put a constant in there to make things work out right. Let's see, the derivative of 2x squared, well, the 2 would come down and make 4, and then you'd have x to 1 power less. And the derivative of negative 2x to the 1/2, the 1/2 would come down, and you'd have x to the negative 1/2. So we'd have 4x, let's see, the 2 and the 1/2 combine to make 1 when they multiply. And x to the negative 1/2 is 1 over root x. So it works. Are there any other possible solutions? The derivative of this works. Well, corollary 2 says if any other function had the same derivative, it would only differ by a constant. So throw in a constant and you can create all possible functions that have that derivative.